Hello everyone, I'm Liu Tianxu. Today I'm going to talk about an open source vector database. Its name is Milvus. Before our slides, we can see how to use Milvus. First, we should download a Docker desktop, and in the containers, we can download the Milvus here. And we can use Milvus just by Python codes. For example, now I'm running a Python code with Milvus. And you can see it's a searching function. Now let's come back our slides. Uh, Here are five sections, and first let's talk about vector database. What is a vector database? It's a specialized database for high-dimensional vector data, and it's designed for similarity search rather than exact matches. And it's optimized for AI or machine learning applications that generate embeddings. And here are some differences between traditional database and vector database. Next, let's talk about why vector database are important. Because AI applications, some recommendation systems, image and video search, natural language processing, anomaly detection should use vectors. And also, if you use SQL-based database, you will face lots of performance challenges. For example, traditional database has uh, ON complexity, but vector database has only a sublinear search time. For example, if you want to learn the words in the real world, such as ships is close to boats, but you cannot search it on a SQL-based database, and vector database can solve the problems perfectly. Next, let's talk about Milvus. It's a high-performance cloud-native vector database. Milvus is an open source vector database designed for scalable similarity search and AI applications. And its detailed information is as below. We can use Python to use Milvus database. And here is an architecture overview for Milvus. And we can see the coordinator includes query nodes, data nodes, index nodes, and the storage includes object storage, message queue, and meta storage. And here are some core components of Milvus. We won't talk them in detail. Next, let's see an experiment searching in Milvus. Here is our experiment background. We aim to implement a complete vector similarity search pipeline using MNIST dataset. It's a famous dataset about handwritten numbers. And here are some key procedures. MNIST data loading and pre-processing with PCA dimensionality reduction, Milvus vector database integration, and performance benchmarking and visualization. Here are our experiment design. The codes, I will put them in GitHub. You can check the details over there. And here is my workflow. Data loading, pre-processing, database setup, data insertion, similarity search, and visualization. And here are the experiment results. Uh, the picture on the left is a query image with ground truth label. And the five right pictures shows top five most similar images from vector database. and the scores indicate similarity. The lower means the more similar. Next, let's talk about indexing in Milvus. As in traditional SQL-based database, we usually use B plus trees to index. However, in Milvus and vector database is different. Now let's talk about our research background. The dataset is SIFTIM subset. It's about 10,000 vectors of 128 dimensions. And our objectives are comparing search speed across different index tabs. The detailed index tabs I will talk in the next slides. Next, we want to analyze the impact of index parameters on performance. Finally, we want to provide guidance for index selection in production environments. Now let's talk about our result 1, performance comparison by index tab. Here are 4 types of indexes: flat, inf, IVF flat, IVF SQ8, and HNSW. In the picture, we can see flat is slowest because it's an exact searching. It's slower than approximate search. And IVF SQ8 and HNSW show best performances. So approximate indexes demonstrate expected speed advantages. Next, let's talk about the impact of search parameters. In IVF flat and HNSW, here are some parameters we can tune them. The key findings are for IVF series, the larger n list, the lower the search time is. And HNSW shows the best performance with M equals to 8 and EF equals to 128. Parameter tuning significantly improves approximate index efficiency. Next, let's talk about some optimization tips. First, let's talk about the selection guide. If you want to a high precision, you can use flat index. It's an exact search. If you want to balanced, you can use IVF flat. It balances good accuracy and speed. If you want to memory efficient, you can use IVF SQ8 and IVF PQ. If you want to a high speed, you can just use HNSW. And below are some contents about parameter tuning. Finally, let's talk about our conclusion. When to use Milvus, the ideal use cases are below. Applications requiring similarity search, AI, machine learning systems with embedding vectors, large-scale vector data management, and real-time recommendation systems. And below are some situations you can consider alternatives. Okay, thank you for your listening. You can find my presentation slides and code examples uh, on my GitHub.